Hello, we continue with systems of linear algebraic equations, but today we will approach it from a new angle, which is actually an old angle, because previously when we were talking about numerical solving of equations, we introduced the notion of a fixed point. And we commented then that it's a very general approach which can be applied to many settings. Well, here we have one interesting setting, so why not trying it? Okay, how do I create a fixed point equation? First of all, I'm going to get rid of b, so I will move it to the left. And now I add x to each side of this equation. And I have a fixed point situation. I will prefer to write it in a slightly different way. I would like to put these x's into one place so that it's just one x on the left, and I cannot factor out. So I will introduce a little trick. This x is actually the same as the identity matrix times x. And now I can write it very nicely. A plus En is a matrix, and this multiplies x, and I get a very nice iterative formula. Unfortunately, this kind of iteration does not really work well for problems that we meet in applications. So we prefer to use a different way to create iterative equations, but this serves as an inspiration. What we will like to do is to do iterations of the following form. We take some matrix and multiply the kth generation with it, and then we add some shift, vector c, and this creates a new generation xk plus 1. So that is a general form for our iteration. And what we see on the right, this is the iterating function phi, but this time it's a function which works with vectors, not just with numbers. So far so good. That's the setting that we saw before. And we used iteration to find fixed points, if we are lucky. So that's an important question. That's the crucial question. Can we somehow recognize the cases when we are lucky when it comes to matrix iteration like that? And the answer is, well, let's follow the familiar path. Let's ask whether this phi is actually a contraction. Again, we commented that contractions are a very general notion, as long as we can measure distances. Well, we definitely know how to measure distances for vectors. So let's see. We apply phi to some x and also to some y, and we look at the distance. For that we have a norm, which we introduced in the previous lecture. Which norm? I don't care. Let's give ourselves some freedom so that we can apply the norm that we prefer. Okay, what's that? Well, here we have the triple norm. Phi x, for that we have a formula. This is bx plus c. And we are subtracting by plus c. And we can see that c cancels, which is nice. And there are two terms, both of them featuring the matrix B. So I can factor it out, and I get b times x minus y in the norm. And finally, and this is where it gets interesting, we split it, we introduce some matrix norm which is compatible with the triple bar norm. And we arrive at the following formula, which is exactly the type of inequality that we like to see when we talk about contractions. We do get a contraction if this norm is less than 1. And then by the Banach's contraction theorem, we do get convergence for our iterative scheme. This deserves a statement. Here we go. If the matrix which determines our iteration has a norm less than 1 for some compatible matrix norm, then our iteration converges, and we have two inequalities there, and they are interesting. Let's have a look at them. The first inequality actually on the left shows the absolute error of the k plus first approximation, or the k plus first iteration if you want. And on the right there is the error of the kth iteration. So this is something which tells us about the order of convergence. Let's have a look at it. Actually, it is proved in exactly the same way. xf minus xk plus 1 is, now xf is supposed to be the fixed point. So xf is the same as bxf plus c. And for xk plus 1 we have a formula. This is bxk plus c. And now we follow exactly the same way, and you can see that we get inequality with the norm of B, but this is a matrix norm, the compatible matrix norm, and here the difference between xf and xk. So this is essentially the proof of the left inequality, and when you play with it, you get the right inequality, and the right inequality tells you that the error of the k plus first iteration can be controlled using what's on the right. Well, it's actually the absolute difference. This is the stopping condition. So you can see that the absolute difference stopping condition has something to do with the absolute error. But usually we don't know the matrix expression in the middle, or often we don't know it. So sometimes this is not all that useful, but it is a useful result anyway. So this is the theorem. Now, which norm are we going to use? The answer is we don't really care, because we care about convergence. Now, we talked about compatible norms in the previous lecture, so I can use any norm here, because what I really need is this. I need for this difference to go to 0. And if it works with one norm in Rn, it will work with another norm as well. So I'm sort of checking different norms and looking at this, at the matrix norm of B, and trying to make it as small as possible. Namely, I want it to drop below 1. Now, when I look at all the possible numbers which can be achieved, I know that these numbers have infimum. And we talked about it last time also, which is the spectral radius of B. And in this way, we get an interesting theorem. It could be seen as a corollary, but it's not. Let me show why. Well, because this statement based on the matrix is just an implication. It says, if the norm is small, you get convergence, just one way. But now we get equivalence. Our iteration converges if and only if the spectral radius is less than 1. So this is much stronger than we have over here. I'm not going to prove it, but I will show a little bit how this comes into the picture. And I will start here, but I will look at this error without the norm. I will look at it directly. So what is the error? Which is actually a vector. It's a difference of vectors. I will follow through this calculation, and I will get B times xf minus xk, which is B times ek, the kth error. And I look at it and I say, wow, this looks nice. Why don't I make another step? This is b square ek minus 1, and so on, until I arrive at b to power k plus 1 times the initial error. And this tells me that xk converges to xf if and only if the power of the matrix k, okay, let me put it with just kth power, converges to 0 as a matrix. This is interesting. Now, this is no longer a question for numerical mathematics or analysis or something like this. This is a linear algebra question. And theory of matrices gives me an equivalent answer. This can be recognized by the spectral radius. And again, for this, we just refer to people from linear algebra. And they are nice. They provide us with this answer. Let me give you just a small indication why there should be some, let's say, relationship between these two things. We will look at a very special case. Imagine that the matrix is diagonalizable, which means that there is a basis of eigenvectors. Let's call them EI. Now, if there is a basis of eigenvectors, it means that the initial error, which is a vector, can be expressed as a combination of them. So E0 is a linear combination of the eigenvectors. What happens if I apply the matrix B to it? Well, I get B and this sum. And of course, I can distribute B inside. We have some rules from linear algebra for that. And when I do it, I will get the first error. That's why I'm doing it. Because Vi is an eigenvector of the matrix B, we know the outcome. We'll get lambda I, which is the associated eigenvalue, times Vi. Let's try again. What's E2? E2 is B applied to E1. So it's a summation here, alpha I, lambda I, Vi. And again, I'm going to move B so that it's next to Vi. And now the action of B on the vector Vi can be replaced by multiplication using the eigenvalue. And we can see that eigenvalues are actually squared now. And quite naturally, by induction, we can easily prove that the kth error, that the kth error is a summation alpha I, lambda I to power k, Vi. And therefore, convergence or divergence, or simply the behavior of this error when k goes to infinity, depends simply on the behavior of eigenvalues. Now, if these eigenvalues are all less than 1, which is exactly what this condition says, then these coefficients, they tend to 0, and therefore, consequently, this whole error goes to 0. On the other hand, if sum of the eigenvalues is not less than 1, then this part of the summation will not disappear. And because these vectors are linearly independent, the other ones cannot make up for it. That's the beauty. That's where we need linear independence. So we more or less see the equivalence here, but only for the case of basis of matrix B, which has basis of eigenvalues. The general case is more difficult. That's why this is not a proof, just an indication. So this statement essentially tells us how to recognize convergence for any iterative scheme of this form. Unfortunately, evaluating spectral radius is not all that easy, so very often we pass to this matrix point of view, this norm point of view, and you just check on the norm and hope that it will work out okay. Sometimes it does, sometimes it doesn't. That's life. By the way, we'll have a special lecture on the spectral radius next time, so that's really not a very simple question. I think you are ready for specific methods. Let's have a look at them. Here we go. We have a 3x3 system here, and we would like to rewrite it in such a way that we get equations with x1, x2, x3 on one side. I can see it then as an equation for a new vector, and some formulas with xy, x2, and x3 on the other side. And if we approach it equation by equation, then the natural thing is to simply take the first equation and isolate one of the unknowns. Well, for instance, x1, there is no reason to play favorites. So from the first equation, x1 is, well, we start with b1, and then we subtract all the terms which we don't want to see on the left. So it's a12 x2 plus a13 x3. And then to get x1, we have to divide by a11. Let's see, x2. To isolate x2, we take b2, and we subtract the second row with the exception of the diagonal term. So we can see a pattern developing here. It will be a21 x1 plus a23 x3. And then I divide by the diagonal term again. So that nicely fits. And finally, x3 is b3 minus the third row without the last term. And I divide by a33. I changed my system into a new type of equations, and I can see it as equations of the fixed point type. On the right, I have some x1, x2, x3, and I get it also on the left. So I can see it as generations. I have one vector which I for instance guess, and I use these values, I'm going to call them old here, to calculate new values of x1, x2, and x3. And this creates an iteration. Let's try it out. I have a system here, and following the advice, I'm going to use the first equation and express x out of it. So x will be 1 minus y divided by 2. And from the second equation, I will isolate y, and it will be 1/2 -1 negative x. And when I look at it as an iterative scheme, on the right there is the kth generation, and on the left it's the k plus first generation. And these are nice recursive formulas. Let's try them out. Let's say that I start with 2 zeros. So that's my starting iteration or starting generation. Let's move to the first one. I take 0 and 0, substitute on the right, and find the new values, x1 and y1. Let's see. x1 is 1/2, 1 minus 0, so it's just 1/2. And y1 will be 1/2 minus 1, which is -1/2. Wonderful. Let's see. x2, y2. Well, x2 is y1, which is -1/2, and it's subtracted. So it's 3 over 2 divided by 2. It's 3/4. To get y, I take x, which is 1/2. I'm subtracting here, so it's -3 over 2 divided by 2. It's -3/4. Let's try it once more. x3, y3. I take -3/4. I subtract it, so it's 7 over 4 divided by 2 is 7 over 8. For y, it's xk, which is 3/4. I'm subtracting, this is -7 over 4 divided by 2 is -7 over 8. Well, if I were to guess, I would think that xk plus, or xk simply, is a fraction with 2 to k in the denominator, this seems to fit, and 2 to k minus 1 in the numerator. And yk, hopefully, is the same number but with negative sign. And indeed, one can use mathematical induction to prove that this is true. That's the resulting sequence, and we can see that it converges to 1 and -1. By a remarkable coincidence, 1 and -1 is exactly the solution of the original system. So this iteration actually seems to work. Let's give it a name. It's worth our attention. So this is called the Jacobi iteration method. The general formula is exactly this one. I just rearranged it a little bit when I was typing it. So I kept the b part, the right-hand side part, separate. This is b1 divided by n11, move to the right and so on. And I can see the part with x's written separately as the first term with minus in front of it. That fits. And I wrote these summations as 2 sums. The first one starts at the first column and stops one short of the diagonal. That's why there is I missing in the limit of the first summation. And the second summation starts just after the diagonal and goes all the way to the end, to the last column. So that's the Jacobi iteration method. And of course, it has to stop. So we introduce a stopping condition, which is the absolute difference. We are waiting for the absolute difference to drop below epsilon. I use the infinity norm there because it's very popular. I talked about it in the previous lecture. But you can also use another norm there if you feel like it. So that's the Jacobi iterative method. And I would like to somehow put it into the framework that we introduced earlier. So I would like to write this iteration in a matrix notation. Let's have a look at it. On the left, I can actually see formulas for rows of a new vector. So that would be the k plus first addition of a new vector, which has coordinates x1 through xn. Let's see. Again, I can feel that this is a new vector. I can see a new vector here with coordinates that I can read from the rows, from the individual equations. And I can see that all these entries are divided by some special numbers. And these can be represented very easily by matrix multiplication. This is actually a matrix here in front of this, which has 1 over aii on the diagonal. And zeros elsewhere. So that's a diagonal matrix. And this multiplies a vector which consists of the remaining terms. So the first entry is b1 minus the summation a1jxj. But now I'm talking about the kth addition of the vector. So let me introduce this notation. This is the kth vector and the jth coordinate. That's what I've been using in this slide. And finally, the last entry is bn minus the summation anj xk, the jth coordinate. And in the summation, I always skip the diagonal term. Now let's move on. This matrix that I can see here is obviously related to the matrix of the system, but the numbers, they don't quite fit. But this is very easy to fix. When we have a diagonal matrix, we can find the inverse matrix just by taking the reciprocals of the diagonal terms. That's a general fact, a very convenient fact. So I can write this matrix as the matrix consisting simply of the diagonal entries and then taking inverse of it. That's very nice. What do I see here? I can split it as a difference of two vectors. The first vector is just the vector of right-hand sides. Very nice. And the second vector, the formula, should resemble, when you look at it, the formula for multiplying matrices and vectors. Because I am actually going along the rows. I can see it here. I'm going along the row and multiplying the row, the coefficients aij, by the old vector x. So this is a matrix with the old vector sitting over here as a vector, like that. What kind of matrix am I taking? Well, I'm multiplying row by column, like that, and I see this formula here. So the diagonal term is skipped, and then I can see just the given matrix of the system here. And this is happening on every row. So I get a matrix which has diagonal zeros on the diagonal, and aij off the diagonal. That's the type of matrix I can see there. And it is closely related to the original matrix of the system. That's the way I like it. Now, I would like to write it in a more compact way now. And there is something which is an idea which is called matrix decomposition. Every time somebody gives you a matrix, you can always write it as D plus L plus U. Now, D is a diagonal matrix. L is a strict lower triangle matrix, and U is a strict upper triangle matrix. And it's very simple. You simply take the diagonal and put it here. You take the lower left corner and put it here. And the upper right corner is put here. So every matrix can be split in this way. And I can use it here. So what do I see? I see the diagonal matrix D, an inverse of it. Then I can see the vector of the right-hand sides. And this is actually L plus U. This is the matrix which is left after you subtract the diagonal terms. And there is x here, xk, the kth generation of my vector. And that's essentially it. So I will just collapse it into a formula. The k plus first iteration is, and I will change the order a little bit, so it's minus d inverse L plus U xk, and then there will be plus d inverse B. And that's the formula for the Jacobi iterative method. And now we compare it with the general pattern, and we can see that this is the vector C, which of course is important, but it's not decisive for the success. The success or failure of the Jacobi iteration is determined by this matrix, matrix of Jacobi iterative method. So we have a general formula which fits into the matrix pattern, the general theory that we developed, and now everything depends on this matrix B gem. Before we move on, how do I know that iteration which succeeds actually solves my original system? That's a good question. So let's be optimistic, and after all, we have one nice example which worked. So we have an iteration, it produces a vector. Does it solve the original system? That's a good question. Well, let's check. The original vector, the vector which we get, should satisfy equality which places it here and here. The equality looks like this. The final vector is minus D inverse L plus U times the final vector plus D inverse B. That's the equation. If iteration succeeds, then the final vector should work like that, the limit of the x case. I just multiply this equation from the left by D, and I get L plus U xf on the right plus B. And now I move xf to the left, and I factor out matrices, and I get D plus L plus U xf is equal to B. And this is actually the original matrix A of the system. And this confirms that our iteration actually does its job if it works, if it converges. It really yields the solution of the original system of linear equations. That's very nice. How does it look from a programmer's point of view? Well, this is actually not too bad, because this is a very straightforward calculation. This is just two nested loops. So it's very easy to implement. The program is very short if you want to do Jacobi iterative method. Now, how much work does it require? That's a good question. Well, let's have a look at it. I have to calculate some formula n times. Now, what kind of work do I have to do to evaluate just one formula? Well, there will be n minus 1 multiplications, and also n minus 2 additions, and there is also one subtraction. So it's n minus 1 additions, subtractions. So it's altogether 2 times n minus 1 operations here. Now n minus 1 asymptotically is just n, so it's 2n operations. And one division compared to 2n is negligible, so it's 2n operations. So n formulas, 2n operations for each, but this is all iterated. So this is repeated several times. How many times? Let's say capital N times. So the formula for the computational complexity of the Jacobi iterative method is 2n squared capital N. Capital N is a number of iterations. Let's compare it to Gaussian elimination. Well, Gaussian elimination takes 2/3 and cubed operations. So Jacobi is less computationally intensive if 2n squared capital N is less than 2/3 and cubed. And when we cancel, we get that capital N should be less than 1/3 n. So when we are solving n by n system, if the Jacobi iteration runs faster than 1/3 n, then actually it requires less work than the Gaussian elimination. In fact, this is even better slightly because, as I said, the implementation of Jacobi iterative method is easier compared to the Gaussian elimination. So these operations, the overhead, especially the overhead, is much smaller. So a good question is how many iterations? And that's a very good question. And we will return to it later. But anyway, here we have some general idea. Here is an interesting twist. As a programmer, when you look at this formula, you can see that you have to store the vector x actually twice. You have to keep the old vector because you need it in all the calculations. So you keep it, and somewhere on the side you are creating new values. And only after you create the new values, you can drop the old vector. So you need twice the amount of storage for the vector. That's a certain disadvantage, but not really crucial. On the other hand, the fact that you are using the old vector in all the formulas means that you can actually access it in parallel. So if your computer can do parallel processing, then you can evaluate all these formulas at the same time. So it means that when you are talking about computational complexity, well, not computational complexity, but about time, then in fact the time is about 2n, capital N, which is one order better even. So there are definitely reasons why one should look at the iterative methods, because they are less labor intensive than Gaussian elimination. But of course there will be some downside. We saw it repeatedly in this course in numerical analysis that if you want some improvement, you have to pay for it. Let's see. As a human being, when I look at this process, I feel here that I could perhaps do better. When I look at the first equation, I feel that I would like to express y out of it because I would get a nicer formula. Let's try it. This essentially means that I'm switching the order of the original system. So if I switch the order in the original system, I get a new system. And this new system leads to the following iteration. From the first, but now the second equation, I take y. And y is 1 minus 2x. That's a very nice formula. And from this equation, which now becomes first, I take x. X is negative 1 minus 2y. And that's a new iterative procedure, which hopefully will solve the same system as the original one. So let me put k here and k plus 1 here. And let's try the same game with the same initial guess. So we will guess x naught to be 0, y naught to be 0. And let's see what x1 is and y1. Well, x1 is negative 1 and y1 is just 1. Really? Is it so nice? Yeah? Well, I wanted it to be nice. That's why I tried it. Here we go. How much is x2 and y2? I take y and substitute into the formula, and it becomes negative 3 for x2. I take x, substitute, and it becomes 3 for y. Well, let's see. x3, y3. Well, I take y, substitute here, and I get negative 7 for x3 and 7 for y3. This is not very pleasant. Well, by induction, I rather easily prove the following, that y3, well, I can see a clear-cut correspondence here. Yk will be 2 to k minus 1. That's what I get for y. And for xk is just the same number with opposite sign. And this goes to negative infinity, this goes to infinity. So this has shown me two things. First of all, that the Jacobi iterative method can also diverge. And that's the downside of it. That's how we pay for the speed. Well, hopefully for the speed. We still don't know about the capital N, the number of iterations. But we pay for it by reliability. It might easily happen that the iteration doesn't converge anywhere. The second thing which we just see is the sensitivity of the method to the order of equations. We just switched the equations in the system, and from convergence, we go divergence. That's also something to keep in mind, in particular because we are free to switch equations. So we can actually use this to our advantage. When we are given a system, perhaps we might like to rearrange it to improve our chances for convergence. Now, when you look at this example, you may start feeling let's say, a little hint how to arrange equations. Here we diverged, and we feel that it's caused by this multiplication by 2. I have some tentative solution, some approximation xk, and then I take and multiply it by 2. Well, I can expect some increase. Well, there is something which modifies it. But still, this is highly suspect, this multiplication by 2. Here I'm dividing by 2, so I'm making this y case, x case smaller. And then this term steps in and just adjusts the outcome. So this is much more promising. And it is related to the fact that here the diagonal terms are larger than the other terms. And that's a nice intuitive feeling that I will confirm later on. Right now, I would like to look at it and say, okay, that's nice. That's the Jacobi iterative method. We know about as much as we could see. Let's try some experiments. And then we will try to figure out another method. Hopefully better. We will see. So here we have a matrix 3 by 3. I didn't really feel like doing calculations by hand about with such a big matrix. Big in quotation marks, but with a computer I can easily ask for iteration. Here is a Jacobi method specified, and here is the initial vector, which I just, well, wait, these are my favorite numbers essentially. Let's see. I fire it up, and after 28 iterations I got something which is almost 1, -1, and 1, which is accidentally the right answer. So in this particular example, the Jacobi iterative method converged. But it took 28 iterations. Well, let's see, 28 iterations, and n is equal to 3. This didn't really pay off. Probably because these iterations were really quick. So it's a question how the elimination would actually work, but I think it's better in this example. This is a 3 by 3 system. We cannot really expect big savings. But anyway, what if I wanted to know before I try it about the chances of success? Well, the matrix iterate command, which I'm using here, can also, instead of doing the iteration, just create the matrix. So I will ask for the matrix, and I will apply some norms to it, and also the spectral radius. Here we go. So that's the matrix B that we can see over here, given by the formula. And it's also interesting to see it from this point of view. It's actually the matrix of the system, and we just divide each row by the corresponding diagonal term. We will return to it later. And the spectral radius is 0.6, which tells me by the theorem which we saw before that this iteration will succeed no matter what I choose for the initial vector. So choosing 0, 0, that was for convenience. If I chose another one, it would also give me convergence. That's very nice. However, the spectral radius, as I commented, is not easy to evaluate for large matrices. So we usually try some norms. Here we have a bunch of norms, 4 of them. Let's see which ones. The first number is the column norm, column sum norm, the 1 norm. The second one is the infinity norm. So that's the second number. The third number is the Frobenius norm. And the last number, the fourth one, is the Euclidean norm, the induced Euclidean norm. And we can see that the number which is smallest is the Euclidean norm. But none of these numbers actually dropped below 1. So if I just applied a norm to the matrix B, I would be mildly pessimistic. But not totally pessimistic, because these numbers are really close to 1. And we know that the spectral radius is most likely significantly, or at least smaller by some amount. So I would be okay, I would be on the fence. I wouldn't know really whether to expect convergence or divergence if I just look at the norms. Okay, let's try another method. Here we go again. We have seen this picture before. Sometimes I wish that this Blackboard had a copy and paste capability. With the Jacobi iterative method, we have a vector x1 through x3. We substitute it into the right-hand side, and we get a new addition of this vector. So, can we improve on this idea? Well, let's have a look at it. I have the old version or the present version, but it's longer, so I will call it old version. I substitute and I calculate x1. Now I will try to calculate the new x2, and I look at this formula and I say, okay, x3, I have to use the old one. I have no choice there. But I already calculated new version of x1, and hopefully I hope that this is a better version, that it's closer to the actual solution that I'm looking for. So why don't I use the new addition of x1 in my formula? This looks like a good idea. Now I'm calculating x3, the new version, and I'm using x1, x2. For those I have new values, the updated values already available. So I feel that this should be a better idea, a better iteration, because I'm updating all the values as soon as I see them. As soon as I calculate them, I already use them in the new calculation. So I'm sort of like skipping ahead. With the Jacobi iterative method, I would be still using the old values here. I would get x new. But I'm using x new now, so it's actually that I'm doing the next iteration already within the first one here with this new method. So this looks very optimistic. Let's give it a name. This is called the Gauss-Seidel iteration. And now it actually pays off that we split each row into two summations, because now we can distinguish the old guys, that's the xk vector, which we can see on the right, and the new guys, which is the xk plus 1 vector, xk plus first, that we see in the summation on the left. Again, let's develop a general formula using the matrix notation. And we know how we should start. So we have a vector x1 through xn. This is the k plus first addition. And it's equal to, and we know that this is the diagonal matrix and an inverse. So this takes care of this division. Then there is the left-hand side vector. And now I'm subtracting. And we have to be careful here. Well, okay. Let's start with the new one, because that's how it is in my formula. So where am I using the new vectors? Well, that's the k plus first iteration here. In the first row, I am not using them at all. So I get zeros in the first row. Let's have a look at the second row. In the second row, we do use the new addition of the vector, but just the x1 value. So in order to use the x1 value, we have to put the coefficient here, which is a21, and the other values of the new vector are not used at all. In the next row, we are using actually two values of the new vector. So I would see a31 and a32 here, and then zeros. And finally, in the last row, I see just the new vector, but of course with the exception of the diagonal term. So there will be an1 through an minus 1. So that's the matrix which multiplies the new addition of my vector. Now let's see the old one. So that's the kth addition of x1 through xn. For the first formula, I'm using exclusively the old version, apart from the diagonal term. So there is 0 here, and a12 through a1n. In the second row, I am using a1 in the new addition, so there is 0 here. The diagonal term is skipped, 0 here. And then there will be a23 through a2n, and so on. And we can see the pattern developing here. In the last row, I am not using the old version at all. And I should close this bracket and this bracket. So now we are ready to write down this formula. Let's see. The xk plus first iteration is the diagonal matrix inverse times the vector of the right-hand sides minus, and this is the lower triangular matrix from the decomposition. So it's L xk plus 1, and then there's another minus, which we inherit from here, u times xk. That's the upper triangular matrix. And this is not ready yet, because we are using the new vector also on the right. So if you want to see the proper iterative formula, we have to play with it a little bit. So I multiply out this d inverse, and then I take the term with xk plus 1 and move it to the left. So it will be xk plus 1 minus, but this becomes plus, d inverse L xk plus 1 is equal to minus d inverse u xk plus d inverse b. And this form is not exactly pleasant. So what I'm going to do, I'm going to multiply everything from the left by d. And then I'm going to factor out the vector xk plus 1. So there will be d here, and here d disappears, or d inverse. I multiplied by d, and I multiplied by d. And finally, now I can multiply by the inverse of this matrix, and I get xk plus 1 is equal to minus d plus l inverse u xk plus d plus l inverse b. And that's the formula for the Gauss-Seidel iteration. Here we can see the matrix B, GSM, Gauss-Seidel, and here is the vector C. Again, both are important, but it's the matrix which decides convergence. So we will focus more on that one. By the way, I am sort of very easily taking inverses here in all those calculations, also for the Jacobi method. How do I know that they exist? And the answer is, I don't know it. Over here, if one of the AIs is 0, then essentially we can use the Jacobi or the Gauss-Seidel method. We could try to rearrange the system in such a way that we have non-zero diagonal terms. And if it's possible, that's a good news. But in general, again, there are some limitations that we have to be worried about. And one of them is that one of the AIIs could be actually 0. Anyway, here we have our iteration. And again, a good question is, does it really solve the right problem? So let's be optimistic. And let's imagine that the vectors xk actually converge to some xf. And then the vector xf satisfies this equation. We just copy what we have here and put xf for xk and xk plus 1. And now we can play with it. We multiply it by d plus l from the left. So essentially we are going backwards in our analysis. And then we move u xf to the left. We factor it out, this xf, and we get d plus l plus u xf is equal to b, which means that axf is equal to b. So the good news is the Gauss-Seidel method, if it works, it does provide us with a solution of the original system. That's the first good news. The second good news is everything that we said about the computational complexity is still valid here because it's the same formula. So again, when it comes to Gauss-Seidel method, we get 2n squared times capital N. Which means that if we want to hope that this Gauss-Seidel method works better, it has to come in the form of smaller of the uppercase n, the number of iterations. We hope that by sort of getting ahead of the calculations, we shorten the run. On the other hand, and that's interesting, you cannot use parallel processing for Gauss-Seidel method. So if your computer cannot do parallel processing, then you don't have to worry, which is also nice. But otherwise, if you can use parallel processing, then there's a question whether it's better to use Gauss-Seidel, which is perhaps faster, or Jacobi iterative method, which doesn't have the square here if you use parallel processing. So there are some interesting real-life considerations. Anyway, how does it work? Let's test it on our example. And because the basic underlying principles or underlying formulas are the same, I just copied what we had here before. The same system, the same equations which I derived from it. But now, when I'm doing xk plus 1, I'm using yk. But for yk plus 1, I'm already using xk plus 1 because I have it available over here. Let's give it a spin. To get x1, I'm using the latest y, which is 0, and I get 1/2. But now this 1/2 is used to update y. So it's 1/2, 3/2, 3/4, negative 3/4. If we compare it with the previous run, negative 3/4 already appeared in the next iteration. So we really see that this Gauss-Seidel method gets ahead. It's doing here the calculation which with the Jacobi method would be done in the next step. Here we go. x2. I take the latest y, put it here, and I get 7/4. This is 7/8. Now again, comparing to the previous iteration, 7/8 appeared at the next stage for x3. So essentially we skipped one generation of x's here. The latest x is 7/8. I put it here. I get 7. 15/8 divided by 2 is negative 15/16. Now our iteration actually never got that far when we were trying it for the Jacobi iteration, but that would be y4, the one which we just stopped short of. x3. How much is x3? I take the latest y, put it here. This is something like 31/32. And you can figure out y3 for yourself. Okay, I'll be nice. I take x3, I put it here, and I get 63/64 with negative sign in front of it. So again, you can see this converges very quickly to the actual solution. And it converges much faster than the Jacobi iterative method. On the other hand, if we switch the order, if I use the, in quotation marks, nice formulas, I can expect trouble. Let's see. Okay, I'm switching the order, which means I'm from the second equation taking x. And it's -1 minus 2y, the previous addition. And from the first equation, I'm taking y. And I can actually afford to use the new value of x. So it's xk plus 1. Let's see, what do we get? Well, I'm taking 0 for y, so x1 is -1. And now I take this -1, put it here, and I get 3. How much is x2? I'm taking the latest y, put it here, and I get -7. And y2 is latest x, put it here, and I get 15. Let's see. x3, 15, put it here, 31, with minus sign. 31, put it here, 63. So we can see that both numbers actually seem to go to negative infinity and infinity, respectively. And again, the Gauss-Seidel iteration seems to be going this much faster than the Jacobi method. Let's try some experiments with matrices in Maple. Here we go. The same matrix that we had before, the same system, now we apply the Gauss-Seidel method. Just out of curiosity, with the Jacobi it lasted, or it took 28 iterations before the procedure stopped. Now we use the Gauss-Seidel method. We fire it up with the same initial vector as before to have comparable results. And it took 15 iterations, which is roughly half, which is nice. Definitely an improvement, but it's still quite a lot compared to Gaussian elimination when we compare the numbers, just like we did before. And let's have a look at the norms and the spectral radius of the corresponding matrix. So this is the matrix for the Gauss-Seidel iterative method. And we can see that the L1 norm, or the column sum norm, for the matrix B actually came up larger than 1, but the other 3 norms are actually smaller. And you can see, I talked about it in the previous lecture, there is no hierarchy. When we are trying to guess convergence based on the Jacobi method and the norms, then the best answer, the most optimistic answer, came from the L2 norm, or the Euclidean norm. And as we can see here, the second best answer comes from the Frobenius norm. Now for this matrix, the matrix of the Gauss-Seidel elimination, we can see that the best guess is actually obtained by the infinity norm, which is the popular norm. So we are glad that it actually gives a nice answer. And the Frobenius norm and the Euclidean norm, they give the same answer, surprisingly, but this can happen. This is the spectral radius, 0.3, and you can notice that it's approximately half of the spectral radius for the Jacobi method. Jacobi had 0.6, and the Gauss-Seidel has 0.3. And it's half, roughly, a little bit more than half. And the Jacobi took half, a little bit more than half, the number of iterations compared to the Gauss-Seidel. So there is definitely some connection there, but it's not a precise connection, but there is something about it. So the spectral radius really tells you what you can expect from iteration, which is nice. Okay, now another example. This is a 2x2 example. Let's use the Gauss-Seidel method. And as you can see, we get a nice divergence. This doesn't work really well. The coordinates of the vector x, they seem to be going somewhere. They went to 3 roughly with the x coordinate, and then they started to go to negative numbers, and they keep increasing. So this looks like divergence. And let's have a look at the norms. Well, here the norms actually look quite promising. They are really close to 1, especially the infinity norm. So one can feel mildly optimistic. But in fact, the spectral radius is larger than 1. So we do have divergence. But the divergence is very slow. You can see that the vectors here, the iterates, they are increasing at a slow rate, which corresponds to the fact that the spectral radius is not larger than 1 by a lot, just by a little bit. Okay, so let's talk about convergence, because these are good questions. What can we expect? And the fact is that in general, we cannot really compare the Gauss-Seidel method and the Jacobi iterative method. It can definitely happen that the Jacobi converges and the Gauss-Seidel method does not. So that's another example here. A nice 3x3 system, not very exotic. As you can see, the matrix is quite normal. Here is the Jacobi method and the Gauss-Seidel method. Now I didn't ask for the iterates to show up. What we can see here and appreciate is the number of iterations which the procedure took before it stopped. And here is the solution. That's actually a fairly good approximation of the solution of the system. For the Gauss-Seidel method, the iteration stopped after 20 iterations, which seems better, but actually it stopped because the numbers in iteration are too large. There is a check for that in the procedure. And when the numbers get really, really large, we have a strong suspicion that the method diverges. And this is indeed true. So for this particular matrix, which is not very exotic, the Jacobi iteration actually works, but the Gauss-Seidel doesn't. However, when we use iteration and applications, when this system of equations comes from applications, usually those matrices have specific forms, and it turns out that for common types, the Gauss-Seidel method is more effective, which means two things. We know that everything depends on the spectral radius of the matrix, and we have a scale which starts at 0 and goes to infinity, and there is the number 1. Now, for many types of matrices, one can prove that the Jacobi iteration will have its matrix or its spectral radius closer to 1 than the Gauss-Seidel method. What does it mean? It means that if the Jacobi converges, then also the Gauss-Seidel method must converge, and the spectral radius is farther from 1, which means that it's a smaller number, and we will get better convergence. On the other hand, if the Jacobi iteration diverges, then Gauss-Seidel has its spectral radius farther from 1. So it will actually diverge more happily, which we saw over here. Also, the divergence is much faster than the Jacobi iteration. So that's a typical picture that we can expect from matrices. In particular, there is a special type of a matrix which is called triagonal matrices. Do I have some room to spare over here? Yeah, okay, let's talk about triagonal matrices. Triagonal matrices are very simple. These are matrices that have a diagonal, then they have some number off the diagonal, but just next to it, and the rest is zeros. They often come when people solve differential equations, partial differential equations, using numerical mathematics and special methods. Now, for triangular matrices, the spectral radius of Gauss-Seidel iteration matrix is the same as the spectral radius of the matrix from the Jacobi iteration, but squared, which exactly corresponds to this picture. When the Jacobi iteration diverges, then this number is larger than 1. You square it, you get a larger number. But if GM converges, you get a number smaller than 1. You square it, you get an even smaller number. So that perfectly fits. Now, if you remember, we had a formula for error which was comparing the norm of the k plus first error with the previous error. And there was some induced norm and the previous error. And we know that by taking different induced norms, we can actually make this number as close as we want to the spectral radius. So we can imagine that there is a spectral radius here, spectral radius for the Gauss-Seidel, spectral radius for the GIM. Now, when we do several iterations in a row, then this norm gets to the power, let's say, n, if we do n iterations, or perhaps m iterations. So after m iterations, this power here gets m. And if we switch from GIM to Gauss-Seidel, then we actually get even another constant there. So this tells us that the rate of decrease of the error for the Gauss-Seidel is twice as fast compared to the GIM, the Jacobi iteration. When we translate it into this into the valid digits language, we know that if you decrease the error 10 times, then you get an extra valid digit. Then this essentially means, and this is not a mathematical statement now, but just an intuitive statement, that the Gauss-Seidel iteration, if it converges, actually produces valid digits twice as fast as the Jacobi iteration. So that's a practical point of view at this formula. But the question is, what are the chances actually of Gauss-Seidel converging? This is a very good question. So let's have a look. We will generate a 4x4 random matrix. This sets up a system of equations, and then we will apply the Jacobi method to it, but we will just look at the matrix. So we generate the matrix for Jacobi, we apply some norms to it, and then we look at the spectral radius to see whether Jacobi does or does not converge. And then we do the same for the Gauss-Seidel method. Let's see. So for a random matrix, we see divergence for the Jacobi, and we also see very strong divergence for the Gauss-Seidel, 336. That's a very strong divergence. By the way, let's have a look at the numbers above. These are the traditional matrix norms, the column norm, the row norm, and the Frobenius norm. And you can see that they are significantly larger than the actual spectral radius. So if we went just by the norms, our picture wouldn't be very good. That's life, unfortunately. Okay, let's try for more matrices. So here is another matrix, and again divergence for Jacobi and divergence for Gauss-Seidel. Another one. Divergence again. Another one. Divergence. Well, this one is close actually. 1.6, 1.8, 89. That's nearer to 1 than before, but it's still divergence for both methods. And as you can see, well, this is the first time actually that the Gauss-Seidel was closer to 1 than the Jacobi method in the spectral radius. So it can happen that the Gauss-Seidel does not follow this picture. I didn't say it cannot happen, but it happens quite rarely, as we can see in our experiments. So here we go. Again, Gauss-Seidel now is farther from 1, and we have divergence for both methods. So we tried, I don't know, 5, 6, 7 examples, and so far we never got convergence out of this. And typically, the Jacobi iteration method has spectral radius closer to 1 than Gauss-Seidel. So that's what we learn from this picture, from this experiment, that actually getting those iterative methods to work is not easy. For a randomly chosen system, essentially are out of luck. Fortunately, in applications, we are not working with random systems, but they usually follow some pattern. And it's useful to identify patterns for which these methods work, and it would be nice to see that pattern from the system itself, not from the iterative matrix, let's say the Gauss-Seidel method. And to see that, we will return to the Jacobi iteration because it's easier there, and we look at this matrix notation that we had here before, but in a slightly different way. Let's have a look. We return again to the familiar formula. Here, this is for the Jacobi method, so from the old values we are creating new ones, and we would like to see the matrix of iteration for the Jacobi iterative method. So, how do we use the old vector? To get the first coordinate of the new vector, we use, well, we skip the diagonal term, so we have 0 here, and then we take the terms which are off the diagonal with negative sign, and we divide all of them by the diagonal term. So there is minus a12 over a11, and so on, minus a1n over a11. And then for the second term, we do the same. So we skip the diagonal, and we can see the pattern developing here. We take a21 with negative sign, divide by a22, that's the division here, and we do it also for the other guys over here. So finally, in the last row, we can see a n j over a n n with negative sign. That's what we see in the last row. Now, we would like to recognize convergence of iteration which corresponds to this matrix. So let's backtrack a little bit. Convergence. How do we get it? Well, we have a theorem. This is equivalent to the spectral radius of our matrix to be less than 1. But because we don't quite like spectral radius, especially for large matrices, we prefer to check some norm, and the infinity norm is a good candidate. So we would really love to see the norm of the iterating matrix for Jacobi iteration to be less than 1. That's our aim. But now it's just an implication for the convergence. Well, where do we see the infinity norm here? Well, we should sum up the rows in absolute value, of course, and they take the maximal one. So when is the maximum of the sums of the individual rows? When is this maximum less than 1? And the answer is when all these summations are less than 1. So we have equivalence here again, and we want the sum of what? That's a good question. We are summing up absolute values of these terms. So it's aij divided by aii, but we are not summing through i's. And we hope that this will be less than 1. Now we move aii to the other side. This should be true for every I. So the summation of terms in the ith row, but with the exception of the diagonal one, should be less than the diagonal term itself for every I. So let's put it together now. When we look at the matrix, now these are the coefficients in the matrix of the system. So when somebody gives us a system, we just look at it, and we see that the diagonal term is always larger than the sum of all the other terms in the same row. Then by going through implications, it turns out that the Jacobi iteration converges. So let's have a look at our example here. The diagonal coefficient is larger than the sum of the other coefficients in every row. That works. So by our observation, we could expect the Jacobi to be convergent just by looking at the system, which is wonderful. When we switched the order and we got divergence, well, when you switch the order, the diagonal is 1, and here is 2 off the diagonal. So that's the exact opposite of what we want, really. Now, again, this is just an implication. So it actually happens that very often you get convergence even when this very strong condition is not true. So just going intuitively, I want to see, when I see a system, I want to see the diagonal to be strong. And if it is so strong that it overwhelms the sum of the other terms in the matrix in the same row, then you can be sure that you have convergence. But if it's just strong in some other, in a weaker way, then you have a very good chance of convergence. You don't have a guarantee, but a very good indication. So the diagonal, the strong diagonal, is something that you really want to see in your iteration. Let's confirm it. Here we introduce two notions. The first one is the notion of a strictly diagonally dominant matrix. And when you look at the condition, it's exactly what we have over here. Then there is a second notion which is also useful in applications, but it's not so easy to recognize just by looking at the matrix. This is a more advanced notion. Matrix A is positive definite if it satisfies a certain condition. Now, this condition is really not easy to see from a matrix itself, but it can be tested, for instance, if you know the eigenvalues and they're all positive, then you have a positive definite matrix. What's more important, when people use iteration in applications, they know something about the matrix because the application tells them something about it, and this positive definiteness is something that they get from the application. So again, that's a popular property to have when you apply matrices to, let's say, physics and other situations. Let me just explain in some way, intuitively, what I see when I hear a positive definite matrix. I see this. When I have a matrix, I have a mapping which takes a vector and sends it to another vector. So there is a vector space, there is another vector space, let's say R to N, R to N, and I have a vector here, and I apply matrix A to it by multiplying it with A, and the matrix A can do all kinds of things to this vector. It can enlarge it, shorten it, it can turn it, rotate it, so there will be some vector here called AX. Now, I can compare the position of the vector at the end with the one which I have here. I can somehow investigate what happens to vectors as I'm moving them using the matrix A as a mapping. The condition which is in the definition, the one with X transposed times AX, can be actually written in different ways. And one way, which I want to look at, is this. It can be written as AX dot product X, and this should be positive. Or if you want, AX X, and this should be positive. Now, dot product is used in determining the angle. And the fact that dot product is positive means that the angle between these two vectors is less than pi over 2, or 90 degrees if you prefer. So essentially, positive definiteness means that when this mapping sends a vector, it cannot rotate it so much that it starts pointing in the opposite direction. When you have a vector, you can create a half plane or half space of vectors which point in more or less the same direction. So there is the vector X, and these vectors, I can imagine that they point in roughly the same direction. But these vectors, they point in sort of opposite direction. Now, I'm not using the word opposite in the literal sense, but in let's say, fuzzy sense. So the whole space now splits into two halves. Here is one half space, here is another half space. And positive definiteness means that this mapping never turns a vector to this other half in its orientation. So that's positive definiteness as I see it. Okay. Yep. Now, the crucial theorem, or the useful theorem. If you have a strictly diagonally dominant matrix, then Jacobi and Gauss-Seidel iterations converge. That's perfect news. And in a way, this is a proof for Jim. For Gauss-Seidel, one can do a similar proof. If A is symmetric and positive definite, now symmetry you can see just by looking at the system. Is that a symmetric situation? Yes, that's a symmetric situation. And positive definite, then you have convergence for Gauss-Seidel, not for Jacobi iteration. But in applications, people usually prefer Gauss-Seidel, actually. So that's a guide how to recognize situations when we may want to use iteration instead of elimination. Let's have a look at some practical experiments again. First, we are going to generate a matrix, random matrix 100 by 100, But I want to ensure convergence, so I'm adding identity matrix to this random matrix. It's a very strong identity matrix because I'm multiplying it by n/3, where n is the dimension. So this resulting matrix is not surely, but with high probability, strictly diagonally dominant. I want it to be fair, so I give it a chance. If I put just n here, then I will definitely get strongly diagonally dominant matrix. But I think it would be, a little bit too unfair, so I put n/3, which gives the procedure a chance to sometimes not be very nice. Okay, here what we do is we apply matrix elimination and back substitution, the way we learned it 2 lectures ago. What's interesting, we time it and then look at the error of the solution. And afterwards, after we are through with it, we generate a random vector to start iteration, and we apply the Gauss-Seidel iteration. And we will see what happens. So here we go. First, elimination. It's a 100 by 100 matrix. Elimination lasted half a second, and the error is 10 to negative 14. Now, let's have a look at Gauss-Seidel iteration. Gauss-Seidel iteration lasted, 0.2 seconds, which is about, 1/3 of the time of the elimination, roughly. The solution which it produced has a comparable error, and just out of curiosity, it took 15 iterations. Now, if you remember, judging just from computational complexity, the effectiveness of iteration is better if we have this inequality. Now, in our experiment, n is 100. So if the number of iterations is less than 33, then iterations should be better if they work. And here the number of iterations is 15, so definitely we expect faster run, and it works. Okay, let's try another one, because one experiment doesn't really prove anything, and 50 experiments don't prove anything either. Well, you can see, and that's interesting, again 15 iterations. This seems to be consistent, and that's a general experience. For diagonal matrices of similar type, we get similar runtimes. This time, actually, elimination was quite faster than before, but still slower than the Gauss-Seidel iteration. And again, comparable errors. By the way, errors. How is it with numerical errors? Well, actually, iterative methods are self-correcting. Let's say they do make some numerical errors when they're determining a new vector. Well, when you use it in the next generation, then this iteration is actually supposed to improve your guess. So if you make a little error, it will be corrected. So essentially, as long as the corrections are stronger than the errors that you make, you will be improving, but eventually you will sort of reach a plateau where the errors which you generate are of the same order as the corrections. And that's exactly here. That's the level of 10 to negative 14 or 15 roughly. Okay, a few more experiments. Again, 15 iterations, remarkable. And again, it seems that the iteration is about 3 times as fast as elimination. And the error is usually about 10 to negative 14. Now, this computer seems a bit faster than the one I have at home. What happens if I increase the size of the matrix to 200? Elimination depends on n as n cubed. So the runtime will be roughly 8 times longer, which should be about 4.5 seconds. Let's see. Well, 4 seconds, that's quite good. Elimination, well, 0.7 seconds. Now you can see the difference between elimination and the iteration getting larger, because n grows at a certain rate, but capital N, the number of iteration, grows slower. That's a general experience. Very nice. Again, you can see the error around the order 10 to negative 14. We are using partial pivoting with Gaussian elimination to keep the error down. Of course, definitely, we want to do that. Again, about 4 seconds for elimination, 0.75 seconds for iteration. This is really very nice. Let's waste another 4 seconds on elimination, and here we go, iteration. So you can see for strictly diagonally dominant, or even just diagonally dominant matrices, iteration seems to work much better than elimination. And these are actually fairly small matrices. I mean, 200. That's not very large by standards, by industrial standards. You can have even matrices million by million, and then the difference is really huge. Do I dare to increase it for to 400. It would be half a minute. Okay, let's try it. This will be, yeah, a bit over half a minute. So while this is running, I will make, okay, I will simply wait. And we will cut this waiting time, probably, hopefully. Computer is working hard. That's nice to see. Yeah, just work, just work. Okay. Now it would be a real downer if after waiting half a minute for elimination, well, half a minute, almost precisely, it turns out that Gaussian iteration actually, the Gauss-Seidel iteration actually diverges. That would be a real pity. Well, let's see. No, it converged. Okay, and it lasted 3 seconds. Now 3 seconds versus 30 seconds. Now you can see the improvement. I will return to this topic later. What those experiments show is that iteration is a viable method. Before I move to the last section of today's lecture, let me revisit, or let me go back to one interesting idea that we saw when I was talking about fixed point iteration for functions. Geometric interpretation, that's a very good question. Here we go. When we see a 2x2 system, I actually see 2 lines here, 2 lines in R2. This will be line 1, this will be line 2. I'm not going to draw precisely these 2 lines, but something which resembles them. So the first line, this one, has a rather large negative slope. So it looks somehow like that. While the second line has a negative slope which is close to, well, it's negative 1/2. So let's say that it's somehow like that. So this is the first line, and this is the second line. Now, how do we interpret Jacobi iteration? We are sitting at some point xk, yk, let's say here. What do we do? Well, first we look at the first equation and determine x based on it. So at this moment we use y as it is given, and because y is fixed, it means that we are moving in the horizontal direction. So we fixed y, which we see over here, and we determine new x based on this line, which means that the new x is over here. That's the new value of x, xk plus 1. And here we can see xk. We also need to determine yk plus 1, and we do it independently. That's the beauty of Jacobi iteration. We can do it in parallel. So I have xk, yk. Here I can see yk. Now I look at the second line, and using xk as a constant, which means that I'm moving up in the vertical direction, I find new y. So I'm moving in the vertical direction, and this will be my yk plus 1. So I know yk plus 1, I know xk plus 1, and they determine a new point, which is over here. And this point is xk plus 1, yk plus 1. Now, how did I get there? That's a good question. From the point xk, yk, I moved horizontally to line L1, or the first equation if you want, and then I moved vertically. At the same time, I moved vertically to the second line, and then I moved horizontally. And when these two meet, they produce the new vector. So that's the geometric interpretation of the Jacobi iterative method. You are sitting at some point and you split and you meet again at the new point. So again, we split. First horizontally, then vertically. Horizontally, vertically. Vertically, horizontally. Here we meet. That's our new point. Let's try it again. Horizontally to line 1, then vertically. vertically to line 2, then horizontally. This is the new point. And you can see how this goes. I can see a very nice convergence in this picture. What happens if we switch the order of the equations? That's a good question. So this now is L1, this is L2. We don't really need the coordinate axis. Just the lines are important. Okay, we are sitting at some point here. What are we supposed to do? We are supposed to go horizontally to L1. Well, here is L1, and I'm supposed to go there horizontally, so I have to go this way. And then vertically. Okay, vertically, it means somewhere here. I don't know where yet. And then I'm supposed to go vertically to the second line. Well, this forces me to go down, and then horizontally in some way. And I can see here the new point. So we are essentially doing the same trick. Splitting, merging, but now we do it in the other direction. We are forced to go out and out again. And you can see the divergence. That's the difference between the order. So that's a very nice picture for the Jacobi iteration. How would it work for the Gauss-Seidel iteration? That's a good question. So again, we have a steep first line and a rather flat second line. And we start with some point xk, yk. Let's see here. We will see later that we actually, in the case step, start on line L2, but the initial iteration or the initial guess need not be there, so let's try it in a general case. How does Gauss-Seidel iteration work? Well, we look at the first equation and we solve it for x, which means that we keep y, and we change x, which means that we move in the horizontal direction. And because we are using L1 to determine the new x, we should stop there. So this is the new x, xk plus 1. And we go horizontally to L1. Then we jump to the second equation. Now we keep the new x and we change y. So we are moving vertically and we use L2 for y. So we move vertically to line 2 and that gives us xk plus 1, yk plus 1. And that's the Gauss-Seidel method. Here we go. That's our xk plus 1, yk plus 1. And as you can see, we really are on line 2. So that's a typical starting situation for the next iteration. So we go horizontally and vertically, we are here. We go horizontally, vertically, we are here. And you can see a very fast convergence of this Gauss-Seidel iteration. And this is really what happened when we are doing this example by hand. Okay, what happens if we switch the order? Well, let's see. The first line now is rather flat. The second one is steep. We start somewhere, let's say on line 2. And we should go horizontally to line 1. Well, we have to go here. Vertically to line 2. And our first iteration is here. Horizontally to line 1, vertically to line 2, well, it's somewhere here, the second iteration. And you can see a very fast divergence. So this corresponds to our experience. With Jim, you are not really going to get more exciting pictures than that, because you always split, merge. With Gauss-Seidel iteration, this actually resembles more the picture that we had for iteration for functions, because there we jumped like that between the graph of the function and the diagonal. So it means that you can get more interesting geometric configurations here. Let's have a look at this picture. Line 2, line 1. Let's say that we start over here, on line 2, for instance. We are supposed to go horizontally to line 1. Well, I'm going horizontally to line 1. Then I'm supposed to go vertically to line 2. Well, here we go. Vertically to line 2, and that's my point. And then again, horizontally to line 1, and vertically to line 2. That's my next point. And you can see a very nice spiral, which is tightening up, and very quickly. So that's a nice pattern to see. If we switch the order, so the flat one is line 1, the steep one is line 2. Again, you start on line 2. And we are supposed to go horizontally to line 1 and vertically to line 2. Then horizontally to line 1 and vertically to line 2. And you can see the spiral again, and it's definitely not tightening up. It's unwinding very quickly. So there are some very nice geometry configurations for the Gauss-Seidel iteration. And that's it regarding the geometric interpretation. Of course, if you have more equations, like we had 3 of them here, you start playing with planes in R3, and it gets really interesting. But it's hard to imagine. Probably I cannot quite imagine. Yeah, I can imagine it a little bit, but I don't know how to draw it. So you can try to imagine it if you want. And that's it. Let's move to the last section. The last topic for today is relaxation, which is a very popular topic, I hope. Here we have a nice iterative formula that we want to use, but for some reason we are unhappy with it. So we introduce relaxation parameter lambda, and we create a new iteration. We take the original one and we assign it a weight lambda. And then we also, to keep things in balance, have to assign another factor with weight 1 minus lambda, and we will simply keep the original vector xk. So how do I interpret it? Well, this is my original iteration, for instance, the Gauss-Seidel iteration. And I am doing average between Gauss-Seidel iteration and another kind of iteration, which is the constant iteration. You simply keep the same vector over and over again, which has a perfect convergence. This is a very nice convergent iteration. So by putting some weight here, I'm sort of hoping to improve convergence of the, let's say, Gauss-Seidel iteration or any other iteration. Let's have a look at the matrix of this new iteration. Well, definitely I can factor out lambda b. And then there will be 1 minus lambda, but I cannot just add it because we cannot add numbers and matrices. So I'm going to sneak in the identity matrix. And again, lambda c is not really all that important at this moment. That's what I'm looking at. That's b lambda. That's the matrix that I want to use in my relaxed iteration. And I can see that it's a compromise between B and the identity matrix. In a way, I'm sort of downplaying the importance of B, like muting all the entries in B and pulling up the entries on the diagonal. So I'm moving B towards the diagonally dominant matrix as I keep making lambda smaller and smaller, closer to 0. Then this becomes closer to 1, and I have almost perfect diagonally dominant matrix versus a very small matrix. That's how I see it when I put the slider lambda and move it towards 0. Surprisingly enough, sometimes the slider is moved to 1 and even farther more, and even farther to the right or to the left, depending which way you look at it. When we feel that the convergence is really good, we can sort of put more convergence, more weight on the convergence that we like, hoping to make it faster even, which is an interesting point of view, and we will see it hopefully soon. Let's see some experiments. Okay, here we have a 3x3 matrix, fairly nice matrix. I apply the Gauss-Seidel method to it, and well, it diverges quite well. Yeah, you can see really huge numbers here appearing in the vectors. That's not good. So here is another method. It's called SOAR, and you will see why in a second, but it's a relaxation. And the factor is 1.0. When the factor is 1.0, I'm essentially taking the original iteration again. Nothing new, so I expect the same outcome, which I did, hopefully. So things seem to work well. let's move the iteration factor, the relaxation factor lambda closer to 0 a bit. How about 0.9? Still not good. How about 0.8? Yeah, we got convergence, 39 iterations. That's not bad, perhaps, I don't know. But it's better than divergence. How about 0.7? 45. It's beginning to get worse again. So 0.8 seems to be a better choice, which was 39. How about 0.81? Oh, that's worse. How about 0.79? 39. So it seems that I cannot make it go faster than 39 iterations, but still I turned a divergent situation, which we see over here, into a convergent situation using the iteration factor, let's say 0.8. It's a nice number. Okay, let's move to the second example. Again, 3 by 3 matrix, so that it's fast and we don't have to wait for the result. We use the Gauss-Seidel iteration, and after 24 iterations we get the answer, which by the way is something like -1, 1, -2. That would be the correct solution. Now let's try the relaxed procedure. So 24 is the benchmark. Yes, it works. Let's move to smaller lambdas, let's say 0.9. We got 30, which is worse, so we are actually moving in the wrong direction. So let's move in the opposite direction. Let's increase lambda to 1.1. We see what happens. 18, that's better. 18, how about 1.2? 12, which is half the number of iterations compared to the original iteration. How about 1.3? This is worse again. So it seems that 1.2 is about the optimal value. So we saw two situations when relaxation can help. It can take a divergent iteration and turn it into a convergent, or it can speed up the procedure. And then very often we use lambda larger than 1, which brings me to the slide that's here. And we have a formula here which combines lambda times, this is actually the formula for the Gauss-Seidel iteration, which is where we apply relaxation very often. So this is Gauss-Seidel, there is the traditional stopping condition, and there is the name, successive over-relaxation method. Successive over-relaxation. Over-relaxation refers to the fact that lambda is very often larger than 1. So we are actually not taking a compromise, but we are just using EN to push ourselves away in the direction of the faster convergence. That's very nice. Why successive? Successive because, well, you find the right lambda by running the problem successively. Why would you want to do that if you know the answer? Well, it's the same story that we heard before when we introduced relaxation. You're actually not solving the same problem, but you are repeatedly solving similar problems. Because when you are doing applications, usually the underlying physics or other law which you are using stays the same, but you are solving this problem in different circumstances. So the matrix A is more or less the same. Hopefully then, the relaxation parameter which you find for 1 will work also for the other similar matrix. So that's the idea, successive over-relaxation or SOR. To get you some idea how things work, let me first show an interesting theorem, just out of curiosity. If you have a symmetric matrix and you have positive diagonal entries, which is fairly typical, then row of b lambda, which is b lambda for the Gauss-Seidel iteration, is less than 1 if lambda is between 0 and 2 and a is positive definite. So that's an equivalence again, if and only if, which is very interesting. And this tells us that for symmetric positive definite matrices, it makes sense to pick lambda between 0 and 2. That's a nice guide for practical applications. Okay, let's have a look at an example here. What I'm going to do, I'm going to generate a random matrix, 3 by 3, and then I'm going to apply relaxation with lambdas ranging between 0 and 2. It doesn't make actually sense to put lambda equal to 0, so I start with 0.1 and start increasing by 0.1 until I get to 1.9. And we will look at the spectral radii of these corresponding matrices that we have for the iteration. Here we go. So, important line is this one. Lambda is equal to 1. This is the original Gauss-Seidel iteration. And when we look at the spectral radius over here, we can see that Gauss-Seidel iteration would actually diverge. But if we apply relaxation, we get convergence over here in this range. And the best value, at least as far as we are just looking at numbers with 1 decimal digit, the best value is 0.7, because the spectral radius is 0.4, which is very nice, very nice. That would be a really fast convergence. And we can also see that the spectral radii look like a parabola in a way. There is an optimum, and the farther you go, the worse the situation. So that's a typical shape that you can see, or typical behavior that you can see when you play with relaxation. Okay, that was just one example, so let's try more. Okay, here we have, where is lambda 1? Here. A strongly divergent Gauss-Seidel iteration, and relaxation didn't really help. Even here, spectral radius is still more than 1. Okay, another example. This is similar to what we saw before. Here we have lambda equal to 1, divergent Gauss-Seidel, and we can improve using relaxation, and again the same optimal lambda. Well, that's just an accident, of course. Okay, here we can see lambda equal to 1, so Gauss-Seidel iteration actually converges. And when we apply relaxation and we start taking lambdas less than 1, we are actually making things worse. But if we take lambda larger than 1, we can improve a little bit when lambda is 1.1. But if we overdo it, we get a divergence. So again, that's the parabolic shape, so to speak, of spectral radii. And if you play with it, you can see situations like that again, divergence, which was fixed. And again, divergence, which could not be fixed. And here we have divergence, and again, it was fixed. The optimal lambda is between 0.5 and 0.6, somewhere here. So these were practical experiments which show what you can expect from relaxation. It can really help, especially when you're dealing with large matrices. And that brings me to the last topic of today's lecture, which is a fairy tale, so that you can sleep better. Here we go. Imagine that you want to do a search engine. So first of all, you have to index the internet. You have to look at the pages and make a list of them. And this list is very, very large. And there is a certain company which is fairly popular. And this company, which should not be named, sometimes shares data. And once in a while, let me see. Of course, I don't remember it. So I have to go here. In year 2016, actually, I cannot read that properly. Okay. It looks like 130 times 10 to 12. I have some handwritten notes here. Okay. There are that many pages indexed, which is a lot. I mean, this is a really, really huge number. And when they want to store it, they actually need something like 10 to 5 terabytes. Now 10 to 5, this really calls for 10 to 2, which is 100 of something. Now what's after terabytes? I never saw a disk larger than few terabytes. I looked it up, it's petabytes. So after, I don't know, 10 years, when you are buying a computer, perhaps you will have a petabyte drive, but I don't, well, we will see. But anyway, this is an insanely large piece of data. I would need 10,000 computers that I have at home just to store information that those sites actually exist. Insane. Anyway, somebody asks for a site, let's say talking about relaxation, SOR method, successive over relaxation. You look at this index, which takes time, of course, and you find, let's say, 5,000 hits, and you want to present them in some reasonable order. So you have to rank those pages. Ranking. WI is something like a weight. Wait for a page with index I. How do you determine ranking? Well, here's an idea. If this page is really good, it means that there are many pages that point to it, that link to it. So you have a matrix which describes which page links to which page. It's a 0-1 matrix, essentially. And then when you want to determine the weight, you simply sum up all the links. These numbers aij, these are either 0 if a site j does not show or does not link to this one, or it's 1 if it does link. Now, if you do it like that, you may get really, really huge weights. So in order to make things normalized, you divide it by the number of pages. So now the weight is always something between 0 and 1. This makes sense. That's the first step. And you can somehow capture this information, this aij divided by a, you can capture it in a matrix. But this is not all. You may say, okay, but if a site is really important, then the link also should be more important. So here is the idea. You put the weight also here. And you get an equation. Here you get a vector, W1 through W billions, or trillions actually, this is trillions. Okay, I will write just Wn. Here you have a huge matrix, and here you have the weights again. In this matrix, there are lots of zeros when a certain site does not link to another site. So this matrix is almost empty, sparse matrix. And then occasionally, there will be 1 over n, 1 over n, 1 over n, sometimes. And lots of zeros. Now, that's the basic idea. It has to be tweaked a little bit because one possible problem is that you can have islands. You may have rings of pages that link each other, but they're not interconnected by links. Now, how do you determine the weights? Well, you could actually set them up in any way possible. There are infinitely many solutions. So what they do, they introduce artificial linking, which is everywhere, which links all the pages with all pages. So they're essentially adding a matrix of ones, which is divided then by n and weighted. So they introduce some sort of a relaxation, but it's slightly different. So they make weak links between all the pages. This also takes care of other complications. Anyway, what you get is a matrix which is similar to this one, and you get this formula. The weights are determined by weights. That's a nice cycle, which you can interpret as a fixed point equation. Here we go, fixed point equation, which means you can try to solve it by iteration. And if you don't want to invent anything new and extra, and it's not really worth it, you simply go for the Gauss-Seidel iteration. Or you can go for the elimination. Now, remember, elimination is 2/3 n cubed. Gauss-Seidel is n squared times the number of iterations. So there is definitely a big difference, to n squared rather, especially if n is roughly 10 to 13. So these are really, really huge matrices. Now, the good people at Google, I mean at the company which shouldn't be named, they sometimes share data, and they, in 2010, which was the last time they talked about it, I think, or I didn't find anything newer, they mentioned how this works. And they said the following thing. If they wanted to use elimination, they would, of course, get all their computers to work. In those days, when they talked about it, they said they had something like 20,000 computers. That's a computer farm. So I picture 20,000 computers roaming the Great Plains and doing some work. And elimination would take something like, according to the calculations, 10 to 6 years, which is 1 million years. That's that's a lot of time. Anyway, when they tried iteration, it takes about 3 days, which is quite a difference. So obviously, iteration is the way to go. And just out of curiosity, capital N for them is between 80 and 100. So they do this about once, or they used to do it some time ago, about once a month. And after 3 days of fiendish calculations with fiendish matrices, I mean, these are really huge formulas. These numbers are terrible. This is the n. After 3 days of, probably they have more than 20,000 computers now, and they are better, and they get it. Elimination is dead end, obviously. So that's a fairy tale. which tells us that iteration actually can help, and it does help lots of people in physics, in engineering. Probably majority of problems that are actually done in engineering are done in some way by solving huge systems of linear equations, usually by iteration. And of course, there are more sophisticated formulas than Gauss-Seidel, but Gauss-Seidel is, for all its simplicity, surprisingly powerful. And that's the happy end. See you next time.